Is this green?
Okay.
Yes. Oh, I heard myself.
If you don't want it, maybe you can just put it here. It's fine.
It works.
All right, so, yeah, so please go ahead.
Awesome. Thank you. All right. So we did our project on diabetic retinopathy classification and lesion localization. Oh. There we go. So to start, diabetic retinopathy is one of the leading causes of blindness globally, and it's the most common microvascular complication of diabetes. The high blood sugar can harm the retina, causing a blockage of small blood vessels, leading to fluid leakage or bleeding. The retina is the part of the eye that processes light and sends signals back to the optic nerve, and it's how your brain processes images. So to categorize the stages of diabetic retinopathy, it's looked at by the number and type of lesions and abnormalities. So the first picture is just a normal fundus image, and then as we go across, it goes mild, moderate, severe, non-prolific diabetic retinopathy, and you can see progressively there are more hemorrhages and microaneurysms that characterize that particular stage. And then for prolific diabetic retinopathy, we start seeing the growth of blood vessels, and that can just lead to further vision loss. So motivation for this research is that automated DR detection can improve early diagnosis, reduce chance of blindness, and enhance accessibility in rural or underserved areas. Visualizations such as GradCam can provide insight into the model's decision-making process, making everything more interpretable, which is really important for clinical trust. So there have been lots of studies done for developing DR classification methods. It kind of started with like SVMs, and they were using like handcrafted features, which was tedious, and they weren't getting great results. So more recent work has shifted to CNNs, transfer learning, vision transformers, and hybrid models. We were particularly interested in hybrid models that would combine CNNs and vision transformers, because the CNNs focus on more local features, and then with the vision transformers, you're able to get more like long-range spatial information. So main contributions of the project, we are proposing 2 CNN transformer models for DR classification. The goal is to identify the best pre-processing techniques to enhance DR classification, whereas some of the previous related work was using one technique or just regular pre-processing rather than like filters. So our approach is for each hybrid model, we're going to create a model using a pre-trained CNN backbone, and then fine-tune the model using vision transformers and DR datasets. Then we're going to use the model to compare different image processing techniques, evaluate using different metrics, and then visualize all the results using GradCam. So for the first model, the CNN backbone we used was ResNet, and the important components of this were the convolutional blocks, where they will reduce the dimension of the image and then extract features. And then the identity blocks help the model train deeper, allowing information to skip layers. And this effectively detects edges, which is important to identifying the early signs of DR. And then for the transformer component of this, we used a vision transformer variant. So it will take patches of the images, create an embedding, and then do positional encoding to kind of create an understanding of how one part of the retina relates to the other. And then it'll go through the encoder and eventually predict the DR stage. So altogether, we have this hybrid ResNet vision transformer model, where the ResNet is getting more of the fine-grained local features, and the vision transformer is able to capture more of the global relationships.
And for the second model, we used a DenseNet 121 as the backbone, and it has convolutional layers and pooling layers and dense blocks, and each dense block has multiple convolutional layers where each layer receives feature maps from all previous layers. And for this one, we use Swin transformer or shifted window transformer as the transformer component. And it starts by splitting up the image into non-overlapping patches. For this one, it started as 4x4 blocks, and then they're embedded and go through back and forth between Swin transformer blocks and patch merging. And the transformer blocks update the embeddings using self-attention, MLPs, and shifting windows. And the patch merging combines 2x2 neighboring patches, creating a hierarchical structure that captures local features in earlier training and global features as the patches get larger. And combined, we get a hybrid dense Swin model that takes an input image, pre-processes it, and sends it through the DenseNet to capture features, and then goes through an adaptive average pooling layer to get it in the right format for the input of the Swin transformer. And then it goes through there and classifies it. The DenseNet captures the local features, and the Swin transformer captures local and global features. There we go. And the data sets we're using are the Aptos 2019 that has 3,662 labeled images, and the DR detection, or IPACS dataset, has 35,126 labeled images. They all have fundus images, and they're labeled 0 to 4 from no DR to proliferative DR, the most severe. And the experiments that we focused on were comparing and contrasting different types of preprocessing techniques. CLAHI, or contrast-limited adaptive histogram equalization, gives local contrast and exposes fine features, and regular histogram equalization provides global contrast and brings out details in light and dark. And the Frangi and Hessian filters emphasize edges, can help detect irregular structures, and Gaussian and medium blur reduce noise. And by comparing model performance across different techniques, we can evaluate which improve metrics and enhance the visibility of lesions the best. And this is an example of each of those different preprocessing techniques, with the original on the left and then the CLAHI. And you can see that the regular histogram equalization definitely brings out those bright and dark parts. And the Frangi focuses on smaller, vessel, oblong, and the Hessian filter captures more structures. For our initial results, we just trained on the Aptos data set. So we had less training data, but and the best metric for each row is in green. And initially, we found that the hybrid res VIT did not improve at all with our preprocessing techniques. But for the hybrid dense Swin model, all of the best metrics were found in the preprocessing techniques. And here are some examples from our GradCam. And so we use GradCam to display a heat map over the images to be able to see what the model thinks is the most important, what helps it decide its classification. And you can see where in from like left to right, it's like lowest, like no DR to most severe. And like you can see on that, like there's a lot of, you can see like some lesions in the red and yellow on the ones more on the right. And this bottom right one is actually misclassified, and you can kind of see like in the blue there's some lesions that show, oh, the model missed something there. And so it just helps us like understand like how, what it's using to decide. And for our next steps, we're going to add in the IPAX data set with training and testing to give it a lot more images and help generalize and learn better. And we'll be tuning our hyperparameters to hopefully see an improvement in our metrics as well. And add more experiments with pre-processing images, and as well as adding ablation studies to see like which of our architecture factors, like how they play into it separately. And overall, diabetic retinopathy is the leading cause of vision loss. So early detection is critical. And we propose 2 different CNN transformer hybrid models for DR classification and 4 different pre-processing methods. And preliminary results show promise in changing pre-processing techniques for the dense swim model. And some future work like past this semester could be like performing similar pre-processing experience using other models, exploring advanced explainability techniques beyond GradCam that are a little more focused and less broad, like attention-based heat maps or lesion-specific detection. And we could also extend the model to also localize and detect specific lesion types like microaneurysms and hemorrhages using lesion segmentation or lesion detection. And that is.
Thank you. Question? Comments? Anything?
Yeah, I have a question. So, regarding the swine transformer and the vision transformer, so did you use the pre-trained weights, and if that is, then what was that transformer's weight trained on, and if not, then did you like fine-tune it? Like, could you go over that detail?
Yeah. So we used like the pre-trained weights from the CNN models, and then passed that into the transformers and fine-tune on our data with the transformers.
I think that these dense measures, like how competition, how the training, how much time add that to the training, or it was more fast or slower at the end?
With the extra pre-processing?
No, with the module that the new learning that you had, that's one. Like
Oh, with the
configuration is the hybrid network.
of like the dense layers, is that? Yeah. Sorry, I don't think I heard. Ooh,
I think you have to go the other way.
there we go. Like, are you talking about DenseNet? Or,
This hybrid, and then you have the next one. You use this one, right? Hybrid, that's so.
mhm.
When you train that one with can you open now to the last result? You have the graph cam. REST-VAT, which one was lower, or in terms of time in inference or training?
Oh, I think this one took longer. Yeah, it was struggling quite a bit.
So yeah, the res VIT took longer. But we also, at least I didn't do that many epics yet. For this one, we definitely have we're adding more data and adding more epics after today.
Okay, great. So I have maybe one major takeaway or comments for you guys is I don't really get the motivation of this research. So I think I gradually understand, the main focus is the pre-processing. Am I understanding this correctly?
Mm-hmm.
But I don't think you present in a very good way. Why do we care about pre-processing for this task? A lot of time, a lot of images, right? So we just do something very standard, right? Like data normalization, and that's it, right? So, but here, why do you care so much about the pre-processing? Is it because of the data itself, or why is it? So I think that part is not clear to me,
Okay.
right? So can you explain, maybe?
Yeah, so when we were looking at the related work, a lot of them were doing what you said, just like normalization. And then I found one paper that they started exploring with the pre-processing techniques. And I was curious to see how that would affect some of the other models I had read about, just because some of the features are so fine. We're trying to get it to be more specific towards the earlier stages of the DR detection. And
in the related work, we saw them doing different types of pre-processing for a lot of different papers, and so
yeah. So I think in that case, you guys need to maybe in a later report, you need to find strong evidence, right? So also maybe look at the data itself. Different classes, they maybe have very small or not very distinguishable differences, right? Maybe using some pre-processing can enhance that feature or enhance that difference. Then the model can easily to detect that pattern. Right, so I think that will be really justify why you are so care about pre-processing, right? Because otherwise people wouldn't, why do I have to do this, right? I mean, it's good, right? Pre-processing may not necessarily have a lot of computation and can easily make the model learn better. So if you have a strong evidence, right, for this particular type of data, and also for this application, that can really play a major role, then that's justify the motivation. And second point is that, I mean, if you are focused on the pre-processing, then the model doesn't matter, because you don't want to try to prove 2 points, right?
Mm-hmm.
You just want to make a strong point. Okay, pre-processing does make a significant impact on the performance. Then you can take whatever, maybe a couple of them, 2 or 3 or even more, the standard CN, standard transformer, and maybe you can have a hybrid, right? So these 3 kind of major methods, and you do all these benchmark or investigation, and see if there's a consistent trend, right? Okay, I'm trying all these 3 different methods, right? CN, one category, vision transformer, the second category, and also the hybrid. And I observe maybe one particular, pre-processing, let's say Gaussian blur, right? So consistently improve or if yield the best performance, right? For all these 3, or maybe you don't have a winner, right? Then that's your conclusion, right? Do we have a winner or not, right? So I think that's a very clear message, right? Why you are doing this and what's the conclusion based on the experiment you've done, right? So right now it's kind of a little mixed. Seems like, okay, you have the pre-processing, but you also try to bring up some of the network design into the mixed, right? So you want to try this hybrid. But I think the really focus is you want to test out, right? Trying to justify, okay, pre-processing is really important. And out of all these investigations, with all the experiments I've done, I have a very concluded evidence, like maybe 1 or 2 is the the best choice. And then that gives the practitioner or research, right, a certain recipe, right? So this is the recipe. I've done this, and this is the takeaway, the recipe you should follow, right? So that's, I think, the insight people want to get. So that's my, my suggestion for you. Hopefully you can, in the final report, some of the point you can touch upon. Okay.
All right.
Okay.
Yeah.
All right.
Thank you.
Okay. Great. Thank you. Okay. All right. Let's move on to the second. Let's see. Matthew. You are the only one, right?
No, we are the third.
The second group is Matthew.
Yeah.
So are you
Should I
online?
just share my screen?
Okay, give me a second. Yes, please share your screen.
Okay. Can you see it?
Yes.
Alright. So I'm also doing diabetic retinopathy classification and lesion localization. I guess, yeah. So I guess in terms of the agenda, I'll first be starting with my problem statement and my motivation. Then I'll be going into like the related works and things that I kind of use as like motivation and inspiration. Then I'll be going to my data set and the general methodology. Then I'll finally be going to my results, which are still very early, and then like next steps going forward. So my problem statement is basically to just use deep learning to basically classify the retinal images for severity, basically. So again, it's a issue with the eye, basically, in terms of ability to with the eye and the tissue in the back of the eye. So we want to see the severity of those issues. And another component is generally just highlighting the specific lesion, which would, in this case, I would probably be using a grad map or a GradCam map. But in this case, it would basically highlight which areas are being most affected with like a heat map or an attention map. So my motivation for doing this is basically that it's one of the leading causes for blindness, and if recognized very early on, then it's very preventable. If we have a way to visualize or basically show like which sections are very important and contribute to this disease, then we can better understand like what we need to look into. Furthermore, so like my main purpose is basically to make it more transparent and interpretable for doctors. And that's kind of like my main purpose behind attacking this specific problem. It can be really helpful because some of the issues you can run into are like black spots in your eyes or sudden loss of vision or blurred vision. So the consequences can be very detrimental, and thus preventing it can be really, really important for helping one's life overall. In terms of literature review, most of my literature review revolved around the models themselves. In my case, I kind of just use a basic ResNet model and then a basic vision transformer. So to start with the ResNet model, it was basically a pre-trained model that I used transfer learning to utilize the weights because it can take a long time to just process everything. So had like a base model that was my ResNet, and then fine-tuned that basically through transfer learning, and then fine-tuning like the final couple layers. The ResNet basically is a skip connection model that skips between particular layers, which helps for earlier features to be more helpful. This is because during back propagation, the later layers are back propagated early or back propagated first, and it learns more information then. But the earlier layers become less important and thus suffer from a vanishing or exploding gradient. So the ResNet helps to deal with that issue, which is important in our case because each layer can basically learn like there's different sections. So like the first layer might learn the edges, and then it might learn different like sections of the eye, and then like kind of dig deeper and deeper. So it's important to understand, and for the model to learn all of the layers itself. I guess furthermore, for the vision transformer, I was using base 16, which basically which is based off of the paper written. And the biggest difference is basically the base 12 model, which is in the original paper, has 12 layers and 12 attention heads, while mine will have 16 layers and 16 attention heads. And also, furthermore, they use a different type of data. They use the JAX with tuning the data, which eventually got converted to PyTorch sensors, which also added a little bit to fine tuning. And yeah. In terms of the data set itself, I'll be using the Aptos 2019 data set for training and the Kaggle DR detection for testing. Well, to start, I basically split the Aptos one into training and testing, because there was a testing section to it. So the training data set was 3,662 entries with an ID, a diagnostic path. I did an 80-20 split on that, where 80% went to my training and 20% to my validation. And then the testing set just had the ID and the file path. It didn't have a severity ranking from 0 to 4. So it didn't have a label. And in my case, when I checked the labels, basically there was an imbalance in the classes where one class, I believe the 0 class, had 50% of its entries, and the next highest ranking class was 27%, and then 10% in 8 and 5. So I'd use focal loss and balance cross entropy to help kind of deal with that, so that it's more equally distributed across all the classes, and the models can pick up on the minority classes a little bit stronger. This technique basically sums the total amount of entries by the entries per class, and then gives an according weight to said class. So, in terms of the architecture, yeah, so that's basically the architecture where I'll be kind of doing this training, validation, testing on the Aptos data set, and my plan now is to try to do that, or I'll probably do a little more revision on my models, and then move to the DR detection data set, which has significantly more entries, and basically use that for testing on unseen data. And I'll have my 2 models of the vision transformer and the ResNet 50 model. And if I can, I'll try to use LoRa to kind of help with, kind of make sure that no layer is, like, basically that every layer is attended to properly. Yeah. And then for fine tuning my data set, I plan on using network pruning and LoRa to help with fine tuning and making sure that all the neurons are important. Furthermore, I'll plan on doing Bayesian optimization and decaying learning rates, which basically helps so that over time, there's not as much tweaking. It just needs a little tweaking later in the later stages or later epochs. So a decaying learning rate probably helps in that regard. And the Bayesian optimization helps so that you don't have to do like a grid search and check every single combination with hyperparameter tuning, which just helps to be more efficient. And then to deal with overfitting, I plan on using regularization and early stopping and dropout. So, some of the results, it's really early on. So, but they were learning suspiciously too well during training, where they were kind of getting perfect accuracy and a really, really low loss. So part of me is thinking that there might have been some data leakage that went when I was doing the data imbalance class, as you kind of never get a perfect accuracy in classification. So I want to first test this on the DR detection data set to see how well it performs and how significant of a dropout it has, and then kind of go into tweaking and analyzing my models there to see where any potential data leakage or like why it was so high with the testing data set for the Aptos data set, the Aptos 2019 data set. And then kind of my next steps going forward is to use synthetic minority oversampling technique, which basically generates data for the minority classes to help deal with data imbalance. And then furthermore, also to use model explainability techniques such as SHAP or LIME. They can be computationally pretty expensive, which is why it's sometimes not used, but they are very helpful as they basically show the model is pushed to make certain decisions, which is overall just helps it to be more interpretable and for doctors to understand like why the model makes the decisions it makes. Furthermore, I might also I think also like a thing that could be used in the future is to use different vision transformer models or different ImageNet pre-trained models such as an EfficientNet, and compare that to my current models that I'm using. And that's it.
Okay, all right, thank you. Any questions? Comments, suggestions? Okay, all right. So I think the project is straightforward. Yeah, thank you for presenting the details. But I have a similar kind of comments, right? So yeah, I think understand this is not like a pure research project, but as I mentioned earlier, right? At least there's something that can be something very unique. So it's good like you have, I see you trying to do a couple of things that we kind of taught in the class, right? Like the parameter efficient fine-tuning. I see you have this LoRa fine-tuning technique. And also you have some of the, using the loss, like the focal loss, specifically to address this data imbalance issue. So these are all good. But feel like there is something missing that can be your own thing, right? So one suggestion is I also see that you have the next step you mentioned, you try to have, you will explore other, this kind of SMOT, right? So other, handle the data imbalance technique. So this could be something you can bring like your own twist, right? So like all these, right, the standard network, right, the efficient fine-tuning or full fine-tuning, that's fine. But these kind of specifically analyzing or exploring different techniques, for handling this data imbalance issue could be something that is unique to this project, right? So I wish to see more on this. Just like the previous team, they were exploring, right, how the pre-processing technique would help this task, right? So that's kind of like the uniqueness of the project, right? So they want to, specifically focus on pre-processing techniques that could, have a big impact on the overall, performance. I think here maybe something you can also do something similar, right? Like the data, addressing the data imbalance issue could be like a highlight, right? So you all have all these standard stuff, right? These tuning, all these things, but these addressing the data imbalance could be something very unique, right? For your project. So hopefully, you will have some time, to investigate more on this. Okay.
Okay. Sounds good.
Okay.
I appreciate the feedback.
Yeah. But be mindful about the time, right? Because I see maybe you still have a lot of things to figure out, and also have to do some babysitting on the implementation, trying to make sure the data loading, the training, validation, test split has been divided properly, right? So there's no mistakes, right? So you get like 100% accuracy. There's definitely something fishy going on there. So hopefully you can address that issue very soon. Okay. Okay.
Sounds good.
Okay. All right. Thank you. All right. Let's see the next team. Okay. You bring your own laptop?
Yeah.
Okay.
Just
So
present over Zoom and talk
yeah, are you able to join the Zoom?
Oh yeah, I've already joined the Zoom.
Oh, okay. So maybe you share the screen then. Yeah. Because I think the recording is maybe hooked up with my computer, so I don't want to mess up this. All right. So in this case, you mute yourself.
Hello everyone. Am I audible? Yeah. Okay, so yeah, we are the third project doing the same thing. Hopefully we are doing something slightly different. Let's see. Diabetic retinopathy classification and lesion localization. So the motivation is very simple. DR is a disease which affects the eyes. So it's a very common complication of type 2 diabetes. So it usually due to high sugar and it impacts the nerves in the eyes, like the visual nerves. So early diagnosis is really crucial because it's really creeps up silently, and by the time people see like noticeable vision loss, the reversibility or preventative measures don't work that well really. So early screening is really helpful. So as we said, right, classification and localization. So classification is basically a grading problem in this sense here in a DR problem. So we have 5 labels and they are just ordinarily arranged. So for example, no DR, mild, moderate, severe, and proliferative. And these are all retina images. And the second problem that we have is, can we identify lesions? So for example, if this is a retina image, there are different things that might be going on in the retina. So aneurysms, hemorrhages, or these exudates are basically deposits, so hard deposits or soft deposits. This is an image I took from a labeled data set for lesion, which had semantically labeled lesion maps, basically semantic maps, segmentation maps. So the main challenge here with lesion localization is that the images that we see, at least for example in this image as well, the lesion itself is a very small region, and the images themselves are not very high quality. This is a full scale, right? And we can see that, for example, even for this small deposit, it's really hard for us also as humans to really pinpoint or something like this. For example, this is a hemorrhage, but there's a small yellow section here. I'm not sure if it's visible on the screen, where my laser pointer is. And this becomes a challenge in lesion localization. I feel that the images themselves are high enough quality. And there are other challenges as well. For example, like we said, right, I think other presenters have already talked about the Aptos dataset. It has 3,500 images, but the Aptos dataset only has graded labels. It doesn't have segmentation maps. So the only there are only 2 datasets that have lesions localized. One is IDRID. This is openly available, but it has only 500 images. And there's another dataset, but it's behind, it's a privacy restricted dataset. So that is one issue that we see with lesion localization. One is that we already talked about high quality images. And so far, there are no papers which talk about both DR grading as well as lesion localization. And in general, there are not a lot of papers which talk about lesion localization. And privacy constraint, I've already talked about that. So for now, at least for the grading part, the DR grading or classification, we are using the Aptos 2019 dataset. I think we have already seen similar slides earlier today. So simple training validation test split, which has already been provided. There is some class imbalance, and but the same distribution is there in all the splits. So we also did a bit of literature review. So the main problem that the literature already identifies with common data sets like Aptos is that there's a lot of variation in illumination. So contrast is an issue. So I think earlier presentation also talked about this Clahe methods, which basically does equalization for somehow normalizing contrast. So a lot of the pre-processing techniques that have already been discussed are around just adjusting for this diverse images, which is illumination, size, or the part of the retina that it is focused on. So it's mostly around those. So those are all the pre-processing techniques. I will not go over them because I think previous presenters have already gone over them. And the common approaches that are being used are ResNet, InceptionNet earlier, and more recently transformer-based methods. There was an interesting cycle GAN-based method as well, which we found to be like really interesting. So going on to like methodology, I'll pass out to Tariq.
I already. So yeah, thank you, Mukul, for. So basically, I already the methodology kind of like shows the basic idea of what we want to do. Like we have some preprocessing and backbone model architecture like Resonate 18 and 50. Other group also said this. We kind of like using the feature extraction as the transfer learning, and then we can do the DR grading also for the first part. And another part we want to do is kind of like using the backbone model like the MedSam or maybe the UNet to find the lesions localization, but also the Nukul has just said that the main challenge is the data because the dataset doesn't have much more images for the lesion segmentation maps, and some of the datasets though they have some privacy restriction. We try to find those dataset if we getting some agreement with them. So if we get them, then we can also do that. But it's still not we can do in the project scope. We are not sure about it. So that's that total idea of the methodology. So yeah, the next one is the preprocessing techniques that we have already have some preprocessing techniques such as normalizations, very straightforward min-max normalization to standardize the pixel intensity of the images, and also have some geometric transformation. As you have said that the data set has some imbalances issue, right? So we have some geometric transformation to augment the data, like using the translation or maybe flipping, cropping, and some of the normal generalized techniques. So another is the illumination correction because some of the images doesn't have the appropriate brightness or maybe have some intensity related issues. So that's why we kind of have some that illumination correction technique also to enhances the local contrast to get a better output in the DR grading. So for the backbone model architecture, we first we use the basic one, the Resonate 18. It's a very basic model architecture of the residual neural network, and so I already discussed in the class. And so basically the Resonate 18 is very initial version of what we want to try, and as a backbone model architecture to get the feature extraction directly from this Resonate 18 pretrained model. So another is the Resonate 50 model. So basically we use this as a backbone model as a pre-trained on the ImageNet data set. So these are the pre-trained models. So for we want to use the transfer learning idea as we already have those pre-trained model on the trained on the ImageNet data sets. So that's why we want to leverage the learn feature that have been learned through the ImageNet data sets. So as we already have some limited data sets, so that's why we want to use that pre-trained features, as well as we want to do some supervision to get a better output by optimize the network and try to get also the learned features which have been learned from the ImageNet dataset through these backbone models, and also kind of like try to compensate the dataset scarcity problem. So and then we basically what we did is kind of like load those pre-trained model like Resonate 18 and Resonate 50 and the vision transformer based model. Then we just kind of like optimize the network and try to get some output of the tier gradings. So we also plan to use some efficient net-based architectures because the backbone models don't have those capability. Maybe they have some already have some CNN-based architecture. We already have the efficient net. All this is already discussed in the class, and also the LoRa fine-tuning we plan to do on the vision transformer-based architecture. For that one, we want to do that LoRa fine-tuning. And overall, we want to use that. See if we can get more better performance in the feature extraction as well as the performance in the DR grading. So this is some preliminary results we get so far. As you can see that in the left side we have some training configurations. We didn't have much more hardware resources for now. That's why it's only stick up to 50 epochs, and the batch size is 64, and the learning rate is given here. And also for the optimizer, we use the Adam optimizer as a standard. And as for the model performance, we can see that the Resonate 18 did a very good job, and some baseline models also kind of had the similar type of accuracy in the testing and validations. And for the Resonate 50, though the training accuracy drops a little bit, but still it has having some good testing accuracy so far. Unfortunately for the vision transformer, we don't have much more now, but we plan to like increase more epochs or maybe with other, because we only have used the vision transformer based version. So there are also other hybrid version of the vision transformer too. We expect that we can get more good results from it also.
Sorry to interrupt. So I think based on the previous, discussion on some of the results you guys have, I want to make some comments. I know computation is one
Key challenge,
maybe
yeah.
a key challenge, right? So for all these projects. So right now, maybe you can switch to BIP small. I don't know about tiny.
Yeah, maybe we
Still
can
quite
also,
large.
yeah.
And also,
I think we think like the performance is also suffering because the data set itself is
Yeah,
too
the
small
data
and
set is
BIP
small.
based.
It's
is not
small,
very
that's
good.
why.
you mentioned the data set small issue.
Yeah, so
maybe-
these are-
that's why ResNet can perform well.
Yeah, that's what ResNet performance is also good, yeah.
Yeah, so maybe you should thinking about switch to a smaller model, and also that's why maybe prefer a hybrid model, right? Because you do want to leverage some of the benefit from the
Both of the work.
Then, but you have these constraints, right? Because the small data and also the computation, then it's a good strategy has CNN as the forefront to extract very meaningful local representations, but only tune a couple of like transformer layer that can gain some global relationship understanding. Right? So
Yes,
that,
yes.
That could be.
That would be a combined
Yeah,
approach.
so I think that can come along, right?
Yeah,
Because
yeah.
the experiment, study, then this is a natural justification, right? So design.
Yeah, so that's one. Okay, so let's continue from there. Is kind of like we also have some ResNet 50 based model feature extraction, and then we have generated the heat map. And as you can see, that it also shows some promises that yes, it can kind of like getting those features which have some liaison localizations. So as you can see that for the severe ones, that there have some, sorry. So as you can see that for the moderate or the severe one, they have some yellow spots, right? So I don't know if you can see that this is already some yellow spots, and our feature maps kind of like focusing on that. So that's kind of like having promise that yes, that the model kind of getting somehow or the probably to some points that have some yellow localizations for those ones at least particularly. So also for the severe ones, you can see that this part mainly has some lesions, the yellow spots, though very small in the size, but at least model kind of focusing on that part particularly to identify this one as a severe class. So with this, we have some next milestones. So exploring variety-based process, as Professor suggested, that we can have both the combined version to get more good results, and implementing the efficient net is one of our and we want to try to obtain the dataset for the ground truth for the liaison localization, and perform the MedSem or any segmentation-based approach for the liaison localization. So that's overall from us.
Yeah.
I think all of the class now understand the diabetic retinopathy problem.
So I actually had a question. Since we are like focusing more, I don't think like everybody is already doing DR classification. I feel like lesion localization might be a more interesting problem to like explore. So the problem that we right now face is like we only have like few images that are like segmented. So like I don't think like training like segmentation task on it might not be like the greatest. We get the best performance. So like should we go down this route of like generating like pseudo ground truth, like using MedSam or something like that?
Yeah, so I think that's a good way to explore. Right? So and I'm not clear. At least for me, I'm not familiar with like these localization in the literature. So there's no existing database has all these ground truths.
Some of the
it has like there is a IDRID dataset which is like 500 images. There's a FGADR dataset which is like 1800 plus images. It's behind like you have to sign an agreement and send an email to them.
We already signed a request, but many of them still didn't get from
like
them. So
we
are trying to
saw
also
online
get
that
them.
Maybe the authors are not responding. So
Yeah,
the
so if they
access-
responded, then we can do that one.
Right now we only have like 500.
500
images.
is a little bit low for that.
So we need to somehow augment them to like get more data, right? So that's a challenge we face, like scarcity.
So I think this is a
Also, the existing literature kind of like working on this type of data sets, only the 500 images or the not too much data sets.
Yeah, definitely lesion localization, segmentation is really interesting, right?
Because
not just interesting to classify, but actually understand, look at the specific region for more accurate diagnosis.
Yeah.
So, I think you guys can explore like these MedSam, right? These foundation model for segmentation. and see if you can do this kind of few shot learning kind of paradigm, right? So with a couple of, handful of label data, right? So are you able to make it more, accurate? So this kind of few shot learning setting could be also something you guys can think about and maybe explore some of the technique here. But yeah, I mean, I think that's maybe a lot of effort, but I think initial stage you can give some like a preliminary result will be interesting. But I don't know, like down the road, do you think, because we are not the doctors, physicians.
Yes, that's the main.
If we can, based on the experience, maybe manually annotate, but we don't know if that's natural.
Yeah, like
right? So
we can't just look at yellow spot must be lesion.
Yeah.
It'd be good, to create such benchmark, more data available, right, to the public.
That would be very great.
Yeah, but we have some difficulties.
Because we can't serve as manual annotators ourselves.
So we can do the manual, but we need expert to verify. Right, if this is really
correct or not.
Because most of the data set we are seeing have the DR grading for the data set, but the lesion localization data set, if we even have the 3,000 images, is kind of like a very benchmark will be now.
But another thing is maybe just without any, let's just make this challenging, right? So let's just forget about ground truth labeling because that's just too much work or it's not feasible. Can we come up with some other technique? Yesterday, the last lecture, Nathan. Okay, he did the project for the image generation.
Right.
Maybe
I saw that.
Can you do something similar, right? Using the handful of labeled lesion data, maybe do some data augmentation or maybe synthetic data generation, and can help you boost the training data size, then enough to fine-tune like a segmentation model, right? To have a better performance. Then whatever the available ground truth data can only be used as evaluation, right? That like you do some competition, the leaderboard, right? You only often have a dedicated test set. You're trying to see.
So something like segmentation guided diffusion.
You can you can using the mask, right? Segmentation mask, right? And to generate a lot of images. Then using that to fine tune like NetSam, right? So see if the performance will be better, then evaluate that on the test data set. So that could also be something interesting.
Okay.
Okay.
Thank you for your feedback.
Go ahead.
Hello everyone. Today we will present our project NeuroChat. So basically we are building a large multimodal model for visual grounding and visual question answering specifically for neuroimaging. And I am Parth, and this is Ashmal, and this is our project. So basically, neuroimaging is pretty much visualizing and studying the brain for understanding its structure and what metabolic activity occurs in the brain. And basically, it either can be a 2D visualization or 3D. And in 2D visualizations, which is the focus of our project, basically we can view it in like 3 different views, as we can see here. Basically, neuroimaging helps us understand like what are the issues which are happening, and so that developing treatments is basically a lot easier. Next, please. And basically, these are in the form of generally MRI or CT scans, and basically our focus will be mostly neuroimaging for tumor detection, as we said earlier. So basically, for general medical images, visual question answering has been studied before, especially in papers like BioMedGPT, which are revolutionary in this particular field. And specifically, that paper can perform a variety of tasks like visual question answering, classification, report summarization, and so on. Next. Although specifically grounding or detection is something which is lacking there. Brain tumor detection, specifically only with images, is a slightly difficult task due to various complications and different types of tumors and so on. But this paper showed that it's possible to perform this task, so they performed it using YOLO V7 on a curated dataset. All right. So although grounding has been, detection has been performed on tumor images, and VQ has been performed on general medical images, we aim to do both with a large vision language model. So the inspiration for our work is basically this paper, which is called GeoChat, which is a vision language model which performs remote sensing. And it can perform tasks like image captioning and visual question answering on remote sensing images. All right. So the problem statement that we are addressing, particularly in the project, is given a neural image, our objective is to perform tumor grounding, so basically locating where the tumor is in the image, and answering questions which are relating to that image or the tumor itself. So basically, our method, so we perform basically 3 things in this project. First of all, data curation, then training the large language model, the vision language model, and the evaluation. Firstly, there are a few datasets that exist in 2D neuroimaging, which include tumors. Most of these datasets are MRI and CT images, and they do include tumor types. But there are not a lot of datasets with grounding information in these neural images. Also, the view information is absent, so basically, are we viewing it from the axial view or the coronal perspective or sagittal perspective and so on. And there are very few datasets with actually neuroimaging VQA or visual question answers which are included in the same. So basically, we had to address all these issues. So what we did was we collected a lot of data about 11 to 12,000 images, and we used the metadata which was included, which is the tumor type, as well as we manually annotated every single image with the view information, like from what perspective we are looking at it. And with these two data types, we basically prompted GPT-4o to generate 3 types of questions. Basically, if a tumor is present or not, what type of tumor it is, and what image type or what view is the image. Along with that, we also generated a long reasoning caption for each image, which basically describes the image, what tumor it is, what type of the tumor it is, and where it is specifically located. So basically, for that, we had to use the metadata as well as the manual annotation as well as the image itself. We also did manual annotation for bounding boxes, which will be used for grounding later. So basically, to go over quickly what we did for VQA generation, for each image, we generated 3 question answer pairs, as I said earlier, for tumor presence, type of tumor, and the image type. And we went through this already, so we can just skip this. For bounding box annotation, we again performed manual annotation for each image using this RoboFlow framework. Next, please. These are a few examples of the VQA generation. So basically, the leftmost one is basically a long caption, a reasoning caption basically, which tells you like what view it is, what type of tumor it is, and the general region of where the tumor is located. Second one, these two are like basically examples of short questions. So the type of tumor and what view we are looking the image from.
All right, thank you. And before we go ahead, we just want to point that out that these reasoning captions or these long questions and image captions, they're pretty much very important for the LLM or VLM alignment, because sometimes you want this language vision alignment. And whatever the base LLM, VLM you're using, they're not specialized for this task. So you want to have some certain set of descriptions rather than just having a fixed set of words, like this is a certain view, this is a certain type of tumor. So that's why we have these reasoning captions. In terms of dataset statistics, we have the training datasets, which compose of like over 11.6K images. And from them, we were able to curate more than 45,000 question answer pairs. And these pairs are divided in short questions. And you can call another one is a long question, which is the reasoning captions. And then again, we have this bounding box grounding annotations. And the way it will be prompted to a model is that it will, these XY coordinates and like X1, X2, Y1, Y2, they will be prompted along with a question, and then the model will be able to learn that and predict that eventually. So that's a goal. And for test set, we have two data sets that we curated the test sets from, which we're going to see in the future slides. In terms of oral architecture, we are using this Qwen 2.5 VL. It's one of the recent VLM, and it has shown some very strong performance across various benchmarks like geolocalizations and in-journal localization and VQA. So in general, how the pipeline looks like for us is that you have an image, which is an input image, which is passed to this VIT encoder. So the encoder that they use is VIT, but it's not just a normal VIT. They re-engineer that to be able to like have it to various image dimensions and then image resolutions, and then they were able to like incorporate these long videos. So they have some certain set of process. They were able to engineer this VIT, and then this embeddings from the VIT encoder is passed through this visual projector. And the goal of that is we want to have a similar concatenated embedding representation where the text embeddings and where you have this visual embeddings, they both want to have on the same representation, which then LLM takes, because LLM does not understand image now as a number. They understand image as in text embeddings, which has been trained on. And we trained this Qwen 2.5 to have the response like that. And in our pipeline, we make sure that it's just a single stage tuning. We don't like pre-train first and fine-tune first, because we have read some work and they claim that a single stage has like a very comparable performance when you have some lower data sets, lesser one data sets. So we just fine-tune this MLP layer and this LLM with lower fine-tuning to have like a parameter efficient fine-tuning techniques. So this is the oral architecture that it looks like. And this is just a rough overview of some of the parameters that we use. We have some GPU constraints as well. So like we're trying to limit this batch sizes and this learning rates, and we're trying on a couple of things. One important thing here is this image minimum pixels and max pixels. This is very specific to Qwen 2.5. It's that if an image is less than of this dimension, it will upcast it to at least this dimension, and then if image is higher than this resolution, it will lower it down to this resolution, so that there is always a dynamic cap in the images, and the quality of image is not compromised. So this is very interesting in Qwen 2.5. For evaluation pipeline, there is a framework called VLLM. What it does is it really speeds up the inference time of VLMs because it does some QKB caching underlying. So instead of a normal inference, it's like 20 to 30 times faster inference time. So that's what we evaluate our fine-tuned model on. In terms of test sets, we have this data sets brain tumor MRI and brain tumor classification MRI. They have their training chunks and test chunks. We take out the test chunks for both of them, and that's what we use for the testing. And again, for the same test sets, we also manually label them to have certain informations, metadata, and attributes, and we also generate the captions for them. And these are completely independent sets, so there's no overlap between them. And for each data set, we have this image descriptions, tumor presence, and then image view and type of tumors. In terms of preliminary experiments, again, like we said, that we have some of these data sets that's specific to the test set. And in terms of metrics, we are planning to use LLM as a judge for now. So we will be using GPT-4 as a judge, and we will be prompting it with certain criteria like accuracy, answer correctness, and detailedness and helpfulness. And we'll be giving us an average score out of 10 for each response. And then we'll compare with the ground truth, and then we'll finalize overall accuracy. For training, we were after this entire process of dataset curation and this labeling, we were able to start this training process. Still in progress. We are 1 quarter down there, and it should be there by the end of this week, and we'll be able to evaluate that. In terms of next steps, what we want to do is we want to compare this Qwen 2.5 fine-tune that we'll be doing, which we call as Neuroshed, with some other baselines like this Biomed GPT, MedPalm, and this other recent VLMs like Llama 3.2 Vision and Lava 1 Vision. And we again have to compile the results, obviously, and then we also we're planning, because since we know that our question and answers are pretty much straightforward for is there tumor present or not? So why not we just have this additional question type in which we just limit to true false? Is there a tumor in the image, true or false? So we have done some existing works where multiple question type helps. So we want to just see if the same hypothesis resonates here or not. So that's the plan for the next steps, and then that's from our side. If you have any questions, please.
Great, thank you. Any questions? Yeah. You mentioned Llama 1 Vision. So do you plan to train on that as well, on your data set?
Okay, if time permits, we can do that, but honestly, realistically, I think we'll be just testing out the zero-shot performance. But if time allows, then it's possible, it's doable. Yes.
So regarding the prompts, so were you generating the prompt, or there was a slide regarding the prompts?
The architecture, the flow.
Yeah. So were you generating the prompts using some sort of framework such as LangChain or Cohere API, or how are you generating those prompts?
These prompts? Yeah, these prompts. So what we do is, first of all, to have a very rich system prompt, we write it down. We have we write down, and we ask a couple of LLMs to modify it and see if that best captures the type of questions we want to ask, and that eventually does better than the LangChain frameworks. And it usually just surpasses them. If you just ask GPT to generate a prompt, it might not be as rich as if you write it personally and then you give us some information. And that's why while generating these reasoning captions, we also pass the metadata. And the reason for that is if you just ask GPT to just generate a caption for the image, it might hallucinate or it might bring up some information which is not true for the image. But if you restrict that, okay, there is a tumor present and this is like an image view of that disease, and now you can come up with the captions. So there are some control parameters which you can experiment with. So yeah, we designed them.
So is the generation simply like you give an input tuple, there is a system prompt which guides, take this tuple, generate this question answer pair, and is that it?
For the short question and answers, pretty much yes. But what we try to resolve that problem, for each type of question, for example, is there a tumor present or not, we try to generate 10 to 15 set of variations, and we try to randomly assign so that there is no fixed set of prompt. And the reason for that is if you have a fixed set of prompt, there is a chance that the LLM is just gonna learn that up and not just generalize well. So just remove that, we do that. But for the reasonings, these are pretty independent. One thing I would still like to mention that ideally in this domain specialized things, we usually have an interference of domain experts and radiologists and so on. They usually annotate these diagrams and they just verify each of the captions very carefully. It's very important. But for the scope of project, we are just relying on the capabilities of GPT-4, and we hope that it does what we want.
Yeah, I was going to ask you this. How do you verify it, right?
Exactly, yeah. So, yeah, we have a postdoc. We wanted to get in touch with it. He has some radiologists, but we couldn't just find a few.
Another option is you can have multiple LLMs. Right?
Maximum wording classifier, yeah.
Generate a couple of response and find the consistency or consensus, right? So that's going to be another initial. Of course, later for some of the easy cases, right, if you see a very coherent consistency between all these different experts,
yes,
agent, you can call this agent, right, LM agent, then that should give you a very high confidence, right? This is okay, but only if it's low confidence or complex, right? Then you have to feed it. Maybe put that in the second stage, which is as the physicians to verify.
Yes, that was one of the things we had in plan, like the maximum wording classifier. And the actual reason for that is, for example, if it's talking about some axial MRI scan, which is like pretty obvious, we give that. But if it's talking about it's near to this particular tissue and this and that, we do not know that. So yeah, we need to have a framework for that.
Another thing maybe can enrich the annotation is also generate, because we have the chain of thoughts.
Yes.
Can you also give us the detailed reasoning step? Then later we can figure out, okay, there may be some certain step, right, through the chain that can lead to the wrong answer, right? So I think that also can be really useful. So
yeah, and this can also be used for training on a negative prompts, that why not to think that this is an image.
Using like a DPO kind of technique.
And these models like DeepSeek and Qwen, QBQ, they have this chain, they generate the chains, unlike GPT, which does not generate the chains, they just give you a final output. So maybe probably that's also a useful set of information. Yeah. But now we have a pipeline ready and up and running, so there is more room for experiment for us. So we'll see how much flexibility we are able to get.
Okay. Yeah, very good. Another thing is, I think this work is pretty good. And how do you expand it, right? Because you were talking about neurochat, right? So you are doing all these neuroimaging. Can you incorporating not just brain, maybe other organs or body parts, and also maybe CT, X-ray, all these, because you want to build a fundamental benchmark, right? So I mean, you can, but this maybe you have to focus on only like the brain or MRI at least. So I just wonder what are your guys' thoughts on this?
So I mean, for the scope of this project, we chose just neuroimages.
Yeah.
Because first of all, the views and stuff required a lot of manual annotation.
Yeah.
But actually, we have considered expanding it to other parts of the body. But I mean, we need to think more about what steps to take. Basically.
Yeah, basically down the road, we are thinking how we can convert this project in some sort of a publication if it's possible.
Yeah.
So for that, it's very, very much needed, but then that would require way more efforts than.
Yeah. Okay. Yeah, I can help you guys with this. So if you are serious considering down the road, maybe after this course, right?
Yes.
So you are trying to build upon and continue to expand the data set and also maybe the task, right? So here, so we if you want to have a publication, we definitely have to expand expand a little bit more?
One pretty quick idea we had is like right now we have these images which are pretty much available and probably like models like Biomed GPT and they have been trained on. But what we can do is we can take some 3D segmentation images and we can just take out the slices from them and we can just convert them to images and mask and then we can use them as a part of training set. So we were able to get one of the data set, but that data set was like just too big to process it. So we didn't include that, but we have some like thoughts for that as well. If you can just
Yeah. So let's we can have some follow-up discussion.
Sure.
So,
Okay.
You know,
All
I have some. I also have a student working on this, and he's working on the pathology. So maybe we can maybe sit down, discuss, and how we can expand that.
Okay.
Yeah.
All right.
Okay.
Thank you.
Thank you. Thank you.
So I think that's it for today. Thank you guys. Really good job. Okay, all right, thank you everyone. Bye.